Hello everyone. In this video, I'm going to show you my solution for Section 2 of the Math B qualifying exam for the Japanese government MEXT Scholarship 2019. So this is it right here. It's a function I at mn, and m and n are both natural numbers. We have two inductive definitions, and what we're going to have to do is find the value at a certain index and also express 2n and 3n in terms of n. Before doing anything, we need to understand in math, you can have a vector of values. So this way we can have a collection of values. And what's important to understand here for this problem is every item is going to have an index. But it's just important to understand that we sort of have a pairing between the value and its index. And if we add another dimension to this, we're going to have a matrix. So we have our indices here, and we have our indices here. And for every item in this matrix, the index of the value is going to be defined like this, for example. So these just represent an index. So what this means is we can take any index. So let's say 1, 1, which is going to be right here. And we're going to have some kind of value here. So this is going to be I of 1, 1. Right here, this is going to be I of 3, 2. Because m is going to be 3 and n is going to be 2. This might not be the best way to draw it. Basically, what you just need to understand is that this is just going to be a matrix of values where every value will have an index defined by m and n. If we have something like I of m1, how we can visualize this, we have a constant for n, which is going to be 1. So 1 is going to be locked in, and we're just going to move along somewhere here, and m can be whatever. So I of mn can be represented like this. And the same goes for I of 1n, so we're just going to sort of lock in the m at 1, and n can be whatever. So our value can be sort of anywhere on this line. I of m1, the values on this line, are equal to I of 1n, and they're actually defined here as 1, because this is the base case. So all of these x's are going to be 1s. And again, the 1s represent the value of I at this particular two-dimensional position. Okay, now that we have the 1s here, we can take a look at the second definition here. Here, again, I think it's very nice to think about this visually. What we're going to do here, we're just going to take a look at this first part here, I at m plus 1, n. So this means that if we take any m, so for example 3 right here, and we're just going to set n to 1, then we're going to have this value, and the plus 1 means we're going to take a look at the next value. And because the n here can be any value, what this means is if we set the m to 3, for example, we're going to take a look at the value that's to the right of it. And right here we have the same, but for n plus 1. So that means that if we lock in m, n plus 1 would mean that we're looking at the value that's right above it. And we can do this for any m. We're going to look at the value that's above. And this last part is basically a combination. So we're moving to the right by 1, and we're moving up by 1. So if we have this, for example, we're going to move right, and we're going to move up. Okay, so let's start with this index, which is 1, 1. And yeah, let's just start here. So as I said, m plus 1 means that we're looking at the value to the right of it. N plus 1 right here means that we're looking at the value that's right here. Okay, so the value to the right of this index is 1, plus the value that's above is 1. And here we're saying that whatever is right here is going to be this. And 1 plus 1 is 2. So what we can do now, we can actually define the value at this index. and this is going to be 2. This right here is the part where it gets beautiful or kind of fun, because what we're going to do now is sort of move our way up and to the right with this technique. So we're always going to take some random index and add the value to the right of it with the value that's above it, and the result is going to be placed diagonally. So in this case, if we take a look at the index 1, 2, the value that's going to be diagonally up to it is going to be 2 plus 1, which is 3. And we can do this now for every one that we have here. So let's just do 3 plus 1, 4, 4 plus 1, 5. So before we continue, we actually already have an answer, question 1, which asks to express I at 2n in terms of n. So let's take a look at I at 2n. So I at 2n means we're locking in m, the m index, at 2. So we'll have this column here, and let's take a look at the values here. So right here we can clearly see that the values increase by a constant of 1. But we can also see the n index of the value is equal to the value itself. In other words, this whole column, which is I at 2n, is equal to n, which is the answer for the first question. To find a solution to question 2, which is similar, but is now asking to express I at 3n instead of 2n, we're going to have to fill out our matrix. And we're going to do this the same way. So we're always just going to start at some index where we have a value to the right, and we're just going to add these values up and place the result diagonally. So 2 plus 1 is 3, 3 plus 3 is 6, 6 plus 4 is 10, and 10 plus 5 is 15. In a very similar fashion, I at 3n is going to represent, in our little drawing here, this column of values. And these go on and on, of course. Okay, right here we can see that they increase at a growing rate. So at first it's going to be plus 2, then plus 3, plus 4, plus 5, and so on and so forth. What some of you might notice, this looks very similar to what happens if you add up all the natural numbers. So if we just stop here, we're going to have 1. If we stop here at n equals 2, we're going to have 3. We're going to have 6. 1 plus 3 plus 1 plus 2 plus 3 plus 4 is 10, 15, and so on and so forth. And those of you that saw this progression here is the sum of natural numbers up until n might know that there's actually a formula, which is this one right here. So if we plug in any n, let's say 4, we're going to get a value, and the value is going to represent all the natural numbers up until n equals 4 summed together. And this is exactly what our little column here does. So what that means for us is we can simply remember this formula, and this is going to be the answer for question 2. Now, for the second part, we're just going to need to find the value at a certain index, which is going to be 5, 3. And what I like about this solution, this is going to be very easy to do. So we're just going to work our way up until m equals 5 and fill out the rest of the matrix. And right here we can stop because this value is the value of I at index 5, 3. And this is going to be our answer, and thus we are done. So just a few points that I want to make here. First of all, the reason I decided to do this video, I was watching this video right here by Komei. This video really helped me to understand the rest of the problems because I had some difficulties with them. But for this specific part of the exam, I actually managed to find the solution. Komei's solution takes a longer time than just doing it the way that I showed you. But definitely check out Komei's channel and leave a like on his videos. Another fun observation is that what we have here is basically just Pascal's triangle. So this is Pascal's triangle right here. And if we rotate it, this is the exact same thing that we have. So let's just say that this is m and this is n. And as you can see here, the sort of diagonal columns here will be our vertical columns. Okay, that's it for the video. What did you think of my solution? Make sure to leave a like and comment.